Look out into deep space, and you mostly see nothing, just an endless stretch of shadow. But what actually makes an object physically black? The most famous example is a black hole, but its darkness is entirely gravitational. The mass is so densely packed that it warps the surrounding space, creating an event horizon where light is simply trapped by gravity. It literally cannot pull itself out. Down here on Earth, however, gravity isn't strong enough to trap light. When we see perfect darkness in a material, we are looking at something physicists call a black body. This diagram shows how that works. You have incoming light waves of all different colors hitting a flat surface. Instead of bouncing off, every wave terminates inside the material. It swallows all the light without relying on gravity. That swallowed light energy doesn't just vanish. It heats up the material, radiating a specific glow dictated entirely by its temperature. Outside the reach of extreme gravity, the behavior of a light beam is governed by the microscopic architecture of the material in its path. Let's look at what happens when light is already inside something dense and clear, like water, and tries to get back out into the air. This diagram illustrates a water droplet boundary. If a light ray hits the inner edge at a shallow angle, it bends and slips through. But past a strict 49-degree limit, the light gets trapped, perfectly reflecting back inside, a process called total internal reflection. Sunlight enters a raindrop, bends, hits the back wall past that critical angle, bounces internally, and shoots back out. That precise bounce separates the white sunlight into the distinct bands of color we see here. Those massive arches stretching across the sky are the aggregate sum of billions of tiny, rigid geometric rules followed perfectly inside individual drops of water. Fluids trap light with geometry, but solid metals reject it entirely. They don't absorb the light, and they don't hold it inside. This simplified periodic table shows exactly where the best reflectors live. The elements on the left and middle, the transition metals, are highly reflective. Move to the far right, and the nonmetals are transparent, dull, or highly absorptive. This reflectivity relies on the way metallic atoms share a massive, loosely bound sea of valence electrons. Because these electrons aren't tethered to any single nucleus, they move easily across the surface. Look at the density and smooth surface of these solid silver ingots. Inside that structure, the atomic architecture leaves higher energy orbitals open, giving those free electrons plenty of room to roam. When an incoming light wave strikes the surface, the sea of electrons catches the energy. They oscillate in perfect rhythm, immediately bouncing it back out. In laboratory settings, instruments like this spectrophotometer often utilize aluminum mirrors. Aluminum reflects a broader range of ultraviolet and infrared light than silver, and it can be precisely etched with lasers to spread light into specific wavelengths. A mirror surface functions as a highly coordinated subatomic defense system. The incoming optical energy is repelled by this collective electron response before it can ever penetrate the material. To really understand light, we have to look closely at the wave itself and correct a very common misunderstanding about how it operates. This animation shows the physical shape of a wave. A photon's wavelength is perfectly continuous. It can exist in fractional, arbitrary lengths, like 300.7 nanometers, or even 300 times pi. We often think of light in strict, discrete wavelengths because our scientific instruments force it into boxes. A spectrophotometer only isolates a narrow band of plus or minus 0.5 or 1 nanometers, blurring the continuous reality into an average reading. This smooth wave hits a physical limit at the atomic level. Electrons inhabit fixed energy levels, moving only when they absorb or release an exact match of energy. This exchange forces light into discrete units, quanta. Materials reject fractional energy, accepting whole units or nothing. Whether that light is entirely swallowed by a black body, bent into a rainbow inside a water droplet, or perfectly bounced by a metal mirror, the continuous reality we experience is built on billions of discrete quantum handshakes in the dark.